Hello everyone, this is your instructor Asma Mushtaq, and today we will study about the vector analysis. This vector analysis tool is actually used in electromagnetic field theory for the analysis of the electromagnetic waves. Okay, vector analysis involve vector algebra and then orthogonal coordinate systems. And the third thing is vector calculus. Fine. So what is the vector algebra? Vector algebra defines the addition, subtraction and multiplication of vectors. Similarly, orthogonal coordinate systems means such coordinate systems where the axis will be perpendicular to each other. So such type of the coordinate systems are Cartesian coordinate system, spherical coordinate system, and the third one is cylindrical coordinate system. Alright, so three types of the coordinate systems that we will study in the upcoming lectures. Next one is the vector calculus. So the calculus term actually describes the integration and differentiation. So here we will see how the vectors are integrated over a line. This will give us the line integral. Then we will have the surface integral, and finally you will have the idea of the volume integral. Also we will study about the delta operation, gradient and the divergence of a vector field. So this was the overview of vector analysis. Let's just start with the definition of a vector. So how a vector is represented? A simple vector is represented by a bold faced character A with an arrow on the top of it, and this is equal to the magnitude of A into the direction of A. This small vector with the cap on it represents the direction of this particular vector A. So if you are interested in determining the magnitude of a vector, what you need to do, you will divide the given vector with its magnitude. Alright. Whenever we talk about the representation of a vector in terms of its components, let's say if we are representing a vector having three components, it means there are three axes involved, that are x, y, and finally you will have z. And let me just denote it like, if this is certain vector A and it is having the component A into ax hat plus b into ay hat plus c into az hat. So here A, B and C are the three alphabets that actually represents the components of a vector A in the direction of x, y and z. So the direction or the unit vector associated to x-axis is ax hat, and the unit vector associated to y-axis is represented by ay hat, and then the vector that is used for representing the direction along z-axis is az hat. So let's say here a is equal to 2ax hat plus 2ay hat then plus 3az hat. So how we can represent this vector? If you move 2 units along x-axis and then you move 2 units along y-axis, so you will get a plane formed by this. Now all you just need to do is to give it rise or height to this particular point in order to get this particular vector a, and then you can join this point with the origin just to represent it as a position vector. Fine. So if these values were given, you can simply represent the particular vector. All right. How we can determine the magnitude of a vector? So the magnitude of a vector actually represents its distance from the origin. So if we take the example of this particular vector or this particular vector, we can say that the magnitude of the vector a, this is represented by the modulus sign on both sides, and this is equal to a magnitude is equal to a square plus b square plus c square, or in other words you can also say that for the given vector a, you can write it as 2 square plus 2 square plus 3 square and then under root. So on simplifying this, you will get 4 plus 4 plus 9, which is equal to under root 17. So this is actually the magnitude of this particular vector a. Fine. Now let's just discuss the equality of two vectors. So two vectors a and b that are denoted by, let's say a is represented as ax into ax hat plus bx into ay into ay hat plus az hat, and similarly there is the vector b which is represented as bx ax hat plus by ay hat plus bz az hat. Then these two vectors are said to be equal if their corresponding components are equal. So in other words, or in mathematical terms, you will say if ax is equal to bx, ay is equal to by, and az is equal to bz, then both vectors are said to be equal to each other. Okay, equality of the two vectors doesn't necessarily apply or imply that they are identical. Fine. Because in Cartesian coordinates, two displaced parallel vectors of equal magnitude and pointing in the same direction are equal. So if the magnitude and the direction are equal but they are displaced to one and other, but they are identical if only if they lie on the top of one and other. So there might be two vectors that will be having the same magnitude, that can point in the same direction, but if they don't lie on each other, it means they are not identical. Fine. So let's just perform the vector algebra, which involves first operation, that is the addition. So addition of the vectors actually follow the head to tail rule. Fine. So when you add the two vectors, let's say we are given a vector A and we are given a vector B. Let me just draw it somewhere over here, just like that. Now I want to perform the operation A vector plus B vector. So graphically how we can do that? We need to join the head of a one vector with the tail of another vector, and this can be done by dragging either A on B or either B on A. So I will just drag the vector parallel till the point until it reaches to the head of B. So in this way I have drawn the parallel vector to A. Now since the head of B is actually joined with the tail of A, that's why the resultant is obtained by joining the tail of B to the head of A, and this gives us the addition of A and B. This is the graphical approach of the addition of two vectors. In case of the addition of two vectors mathematically, what we need to do, let's say we are having 3ax hat plus 2ay hat plus 5az hat, and similarly B is equal to ax hat plus 3ay hat plus 6az hat. Then we will add their corresponding components. So a plus b is actually equal to 3 plus 1 ax hat plus 2 plus 3 ay hat plus 5 plus 6 az hat. So in this way you can find the addition of two vectors. That is very simple. Next is the subtraction of two vectors. Let's say we want to perform the subtraction of two vectors. Alright, so let's say this is certain vector A, and again there is certain vector B, and I just want to perform the subtraction of A vector minus B vector. Again, vector subtraction can be manipulated just like the addition. So you can perform the subtraction A minus B like A plus negative of B vector. Fine. So let's just see how does it work. You just need to invert the direction of a particular vector that we want to subtract. So this, if B is in direction, its inverse direction will be something like that. This is negative of B. Let me just make it more clear. Let me redraw it. Okay, we were having the vector A like that, and here was vector B, and this is vector A, sorry. Fine. Now what we need to do, we need to invert the direction of vector B. After finding the inverted direction of B, what we will do, we will perform the head to tail rule, and for that we will be using the parallelogram rule, according to which if we want to add the two vectors, we need to join the head of one vector with the tail of another vector, and we can do this by dragging or drawing a parallel vector onto the other vector. So let's just say if I draw a vector parallel to the vector A on the head of B, so it will be just like that. It is parallel to A, and once the head to tail is joined, we can join the head of one vector to the tail of another vector, and this will give us A minus B. Now the vector subtraction follows the same rule in terms of the mathematical terms, where the corresponding vector components are subtracted. So I don't think so I need to explain, or for the simple understanding you can say that if a is equal to 2ax hat plus 3ay hat and b is equal to 5ax hat plus az hat, and I am supposed to perform a vector minus b vector, so what I will do, 2 minus 5ax hat plus 3 minus 0 ay hat, since there is no y component present in the vector b, and then plus 0 minus 1 az hat. Fine. So when I will perform this operation, I will get minus 3ax hat plus 3ay hat minus az hat. So this is the resultant of vector subtraction. All right. Okay, now let's just discuss the position and the distance. Position and distance vector. All right. So let's just assume that if we are having x, y and z, and there is a point P that is actually being or connected with the origin, then any vector or any point whose starting point is at the origin represents the position vector. So OP here is the position vector. OP vector is a position vector, and the magnitude of OP vector gives us the distance from the origin. All right. The position vector is usually represented by R1 subscript, and if there are multiple vectors involved, let's say this is the position vector R1, let me show another position vector, that is R2. Fine. And then if there is a vector starting from the head of R1 and joining to the head of R2, then this vector can be represented by R12, since this is R2. All right. So R12 is actually equal to the vector starting from the point P1 and ending to the point P2. We can also say represent it like that, P1 P2 with the vector sign on it, and this is equal to what? This is equal to R2 minus R1. Always this is very important point to be noticed. So if we are interested in determining the distance vector that start from the point 1 and ends on the point 2, what we need to do, we will subtract the position vector R1 from the components of R2 vector. All right. So for example, if the position vector R1 is equal to 2ax hat plus 3ay hat plus 4az hat, and R2 is equal to ax hat plus 4ay hat plus 5az hat, then R12 distance vector will be equal to the subtraction of r2 minus r1, which will be equal to, I will just perform the subtraction directly, minus ax hat plus ay hat plus az hat. This is actually the in the vector form. If we are interested in determining the distance vector or the magnitude, then we can take the magnitude of this vector. This will give us the length of a vector starting from p1 to p2. So minus 1 whole square, 1 whole square plus 1 whole square. This is equal to under root 3. I hope it is clear. Now let's start the very interesting or important topic of today's lecture, that is the vector multiplication. Alright, three types of the products can occur in the vector algebra. These are the simple, scalar or dot, and vector or cross product. So three types of the vector multiplications are simple vector product, scalar or dot product, and the last one is vector or cross product. So let's study each of them individually in detail. Simple product multiplication of a vector by a scalar is called a simple product. The product of the vector A by a scalar k results in a vector B whose magnitude is actually k times of A and whose direction is same as that of A. So let's say if there is a particular vector A and we multiply it with a positive scalar k, then k into A vector will result into an other vector and its magnitude will be equal to k times of A. The resultant vector B will have the same direction as that of A, since the scalar, if it is greater than 0, will not change its direction. Alright, this was very simple, so I don't think so I need to give an example of for its clarification. Let's study the next multiplication, that is the scalar or cross product. The scalar or dot product of two vectors A and B is denoted by A dot B and it is pronounced as A dot B. Alright, and is defined geometrically as the product of the magnitude of one vector and the projection of the other onto the first one, and vice versa. Thus, let's have a look of this. If this is vector A and here is a vector B, then the scalar product of A dot B is represented as the magnitude of A into magnitude of B into the angle between A and B. Alright, so generally if you talk about the components of a vector, so let's say if we are having a simple vector, we know that this vector will have its component on x-axis as ax cos of theta, and on the y-axis it will have its component as ay sin of theta. So these two are the projections of a vectors basically along the axis. Similarly, if you draw the projection of A on B, you will get what? A cos of theta. This is actually the scalar projection of A on B. Alright, scalar projection of A on B. Alright, if we want to find the vector projection of A on B, what we'll need to do? All we need to do is to multiply it with the unit vector of B as it is lying along the direction of B. So let's just be more specific. what we need, in which component we are interested. From this expression I can determine a cos of theta is actually equal to a vector dot b vector divided by the magnitude of b vector. Fine. So on further simplification you can also say that a vector and then the unit vector of b. This is actually what scalar projection. Fine. Now if you want to convert this scalar projection into the vector projection, all you just need to do is to multiply it with the unit vector of b again, since this projection is along the direction of b. That's why the unit vector of b will be involved in it. Alright, the dot product of the two vectors is positive if your theta lies in between 0 to 90, and if the theta lies between 90 to 180, then this resultant is negative. Okay, this is less than 0 then. All right. Okay, now let's assume that if a vector is equal to ax hat plus ay hat plus az into az hat, and similarly b vector is equal to ax hat plus by ay hat plus bz az hat, then the dot products of the two vectors mathematically is written as ax bx plus ay by plus az into bz. Okay, now why this happens? Because if you notice, you can clearly see we have multiplied the corresponding components that were having the same unit vectors. So the component of along the x-axis are multiplied, and then the components along the y-axis are multiplied, and then finally the components along the z-axis are multiplied, and all the other vectors multiplication is ignored. Why? Because if you take the dot product of ax with ay, then the angle between the x-axis and the y-axis is equal to 90 degree. So that's why cos of 90 is equal to 0, and their resultant will be 0. Similarly, if you take the dot product of ax with az, again there is the 90 degree angle present, so that's why their resultant will also be equal to 0. So when you will multiply the ax component with this whole vector b, you will get only the value of the component that is lying along the x-axis. Same is the case for the rest of the components. So you can write it as ax dot ay is equal to 0, ay dot az is equal to 0, az dot ax is equal to 0, and you can write as ax dot ax is equal to 1, ay dot ay is equal to 1, and az dot az is equal to 1. Always remember that all these vectors are unit vectors that shows the direction of the axis. Fine. Okay, there are certain properties of the vectors dot product that are commutative. So vector dot product is actually commutative. You can say that a dot b is actually equal to b dot a. So if either you multiply a dot b, a to b, or b to a, the result will always remain same. Another property that dot product follows is a dot b plus c, and this results in a dot b plus a dot c. The third product, that is a dot b dot c, actually doesn't make sense and it doesn't exist as well. All right. Okay, now an important or interesting point is the dot product of a vector with itself will give us actually what? A square, or the magnitude square. A square, which is actually equal to the magnitude square. Fine. Similarly, if the vectors A and B are specified in the given coordinate system, then the smaller angle between them, theta, can be determined as, or from the dot product we can determine the theta as A dot B, AB cos of theta, and from here you can write it as theta is equal to cos inverse of A vector dot B vector divided by A vector magnitude and B vector magnitude. Fine. So this was very simple. I hope it is clear. Now let's start the vector or cross product. This is very interesting and we will see different properties associated to it. So let's say there are the two vectors given as A and B. So their cross product A cross B is defined as A cross B is equal to magnitude of A, magnitude of B, then the sine of the angle between them, and here comes also the vector, a unit vector that actually represents the direction. Since the cross product of the two vectors result in a vector quantity, that's why the unit vector involved. Otherwise this portion gives us the magnitude of the cross product resultant. All right, this unit vector is actually perpendicular to the plane containing A and B, and its direction can be determined using the right hand rule. So let's just be more specific. If there is a certain vector A and here is the certain vector B, and this is the theta between A and B, then the cross product of the two vectors actually gives us the area of a parallelogram. This is very important point as well. All right, and the direction of this parallelogram can be determined by drawing a perpendicular on this plane formed by A and B. So this A and B, or any two vectors that are not in the same direction, not in the opposite direction, forms a plane, just like I have highlighted on this. All right, and this is the direction of the unit vector. Now let's just see how we can determine the direction of this unit vector from the right hand rule. So if this index finger points in the direction of a vector A and this finger points the direction of V, then the rotation from A through B gives us, then the thumb points the direction of the resultant vector or the cross product. All right, I hope it is clear. So unit vector obtained from the cross product of A and B is always perpendicular to the plane formed by A and B. This is the important point. And one thing more, once you have obtained the plane formed by A and B, all right, this was certain vector A and this was certain vector B. If you half the area covered by this plane, you will actually get what? This forms the triangle, and in this way you get the area of a triangle formed by A and B. So area of a triangle formed by A and B vector can be found by dividing the magnitude of A cross B. All right, or dividing it into half. Okay, according to the vector cross product, it is not commutative, so we cannot say that A cross B is actually equal to B cross A. It is in fact equal to B cross negative of B cross A. Why? Because the direction of this unit vector will be inverted. Fine. If we want to find the cross product of the two vectors, we can simply use this formula. We can write the direction vectors over here, and then the components of vector A in the first row and the components of B in the second row. So in this way we can determine the cross product. One thing to be noticed, that AX dot AX hat cross AY cross AY hat, AZ cross AZ hat, they all are equal to 0 because the angle between them is equal to 0 and sine of 0 is equal to 0, that's why. But AX cross AY hat, AY cross AZ hat, AZ cross AX hat, AX AY will give us the AZ hat, AY AZ will give us AX hat, AZ AX will give us AY hat. Why? Because if X and Y are perpendicular and form a plane, then Z vector will be perpendicular to the X and Y axis, and same is the case for the rest of these multiplications. Alright, now let's study about the third multiplication of the vectors, three vectors, which is also known as the scalar and vector triple products. Scalar and vector triple product. Okay, when the three vectors are multiplied, not all the combinations of the dot and cross products are meaningful. For example, the product A cross B dot C doesn't make the sense because B dot C gives us a scalar, and then this is merely, it doesn't make any sense because the cross product is actually between the two vectors but not between the vector and a scalar. Okay, other than the product of the form of A dot B dot C, which makes certain sense because the dot product of two vectors is a scalar, and then we can actually simply multiply a vector with a constant, so that is meaningful. But the two most important triple products are the scalar triple product and then the vector triple product. Okay, so let's just discuss them one by one. Fine. So first I will discuss the scalar triple product. The dot product of a vector with the cross product of the two vectors is called the scalar triple product, and it is so named because the resultant is a scalar. A scalar triple product follows the following cyclic order. So A vector dot B cross C vector is actually equal to B vector dot C cross A vector, and this is equal to C dot A cross B vector. Alright, the equalities hold as long as the cyclic order ABC is preserved. The scalar triple product of the vector A, B and C can be written in the form of a 3 by 3 determinant. So I can write it as A vector dot B cross C like AX, AY, AZ, and then BX, BY, BZ, and finally CX, CY and CZ. Alright. This validity can be verified by expanding A, B and C in component form and carrying out the multiplication. Okay. let's just discuss the vector triple product. Okay, since each cross product yields a vector, the resultant of a vector triple product is also a vector. The vector triple product doesn't in general obey the associative law. That's it. A cross B cross C vector is not equal to A cross